Okay.
This conference will now be
So in the
recorded.
previous class, we initially spoke things with respect to some theoretical concepts of the microcontrollers. So we understood what exactly is a microcontroller, what is the difference between a microcontroller and a microprocessor, and what are the options we may end up getting while we have to choose a microcontroller we saw. Then even before that, we spoke things with respect to the general purpose system versus the embedded system. And we also saw the categories of real-time embedded systems. So we have three categories. One is hard real-time, second one is firm real-time, and the third one is soft real-time. So we saw what and all happens in each real-time embedded system, and we saw the examples as well. Then after that, we started with the embedded programming. As I said, a big chapter out of all the things we are going to study. So we were looking into some important terminologies initially. So we understood three important terminologies, one being the host, the second one is the target, and the third one is the cross compiler. So we saw what exactly is a host, what is a target, and what is a cross compiler. So we discussed that. And the host in our case is the laptop. The target in our case is our PixIm Lab board, which has PIC16F877A microcontroller. Then along with that, the cross compiler we are going to use in this module is nothing but the XP8. So then we started with the programming. I initially wrote this program where I had to print the value of x, which is 20. But what happens is we are trying to write a program which is non-OS based. So we are not going to involve the operating system while having the embedded system designed. So because we did not involve the operating system, so we concluded that the return type of the main function has to be void. Then the input main also doesn't take anything. So main function will not take anything as an input. So the input type of the main function is also void. And because we don't return anything, as the return type itself is void, so we will not be returning any value, and hence we also removed return 0 from our normal way of writing a program. Then after that, we had to print the value of variable x, which is 20. Whatever program we are going to write, so we are going to execute it on something called as the microcontroller, which is the heart of the board, the PixIm Lab board. Any program we write from here onwards will be executed on the microcontroller. Now, because I'm executing it on the microcontroller, whatever display I want to do, so it has to be displayed on a screen. So first I had to see whether there is a support for the screen on my particular board, or there is a support for the microcontroller screen with respect to the microcontroller I'm dealing with. So we found different peripherals which are associated to the microcontroller on the board. So we saw the list of the peripherals which we can be programming with the help of a microcontroller. Selected the board, the PixIm Lab board. So out of that, we concluded that it is easy to program an LED, and hence we started with the programming of LED. So initially, the intention was to write a program to turn on an LED. So that is the question we took. I had to write a program to turn on the LED. So the assumption we made was whenever I have to turn on an LED, LED has to be written with the value 1. So that was the first assumption we made. Then we wrote this particular program, but when I execute this program on my microcontroller, it will not turn on any LED because LED here is just an integer variable. I'm not referring to the actual LED which is present on the board. So what happens is any peripheral which is available on your board, that is, it can be LED, it can be SSD, it can be CLCD, it can be switches. any peripheral which is present on your board gets connected to a microcontroller via something called as the port. So not just here. So in case of any given microcontroller, if you are going to connect any peripheral to a microcontroller, that is always via an interface called as port. So port is nothing but group of input output pins. So it's an interface between the external peripheral and the microcontroller, and it is a group of several input output pins. Now any information I want to know regarding the microcontroller, I have to refer its data sheet. So we are trying to understand the PIC16 या 877E microcontroller. I wanted to know how many pins the microcontroller has, how many input output pins it has and all. So I had to refer the data sheet of the microcontroller. So we opened the data sheet. So I told you that the microcontroller has 40 pins in total, out of which 33 pins are only the input output pins. Now these 33 pins are being grouped under 5 different ports. So varying from port A to port E. So I have got 5 different ports. Now port A has 6 pins, port B has 8 pins, port C has 8 pins, port D also has 8 pins, and port E has 3 pins. Then we also listed the names of the pins. For port A it's RA0 to RA5, for port B it's RB0 to RB7, for port C it's RC0 to RC7, for port D it is RD0 to RD7, and for port E it is RE0 to RE2. So these are the information we fetched from the data sheet of the microcontroller. Have you got any doubts up to this? Okay, fine. All right, so let us continue with few more information regarding the microcontroller. So I am having the data sheet open again, and I'm still in the block diagram of 877E microcontroller. Okay, so generally, if you take any microcontroller, okay, we generally say it's a 8-bit microcontroller, it's a 16-bit microcontroller. Have you heard of it? So we say 8051 is an 8-bit microcontroller. So we say it's a 16-bit microcontroller. Now, what exactly is the bitness of a particular microcontroller? Or how are you going to check what is the bitness of the microcontroller? The total sum of pins is not 40. Obviously, it's not 40. Lokesh, were you not there in the previous class when we discussed this? So totally here we have only 33 input output pins. The rest of the pins are for basic configurations like providing the voltage supply, different voltage supplies. Then we have got ground signal to be provided. So we have got all of that. So input output pins you have got is only 33 out of the 40. Okay. Yes, sir. So I was telling that the microcontrollers will be said saying that it's a 40 pin microcontroller. So pin anyways you will get it from the data sheet. But what about the bitness of the microcontroller? We say it's a 8-bit microcontroller, it's a 16-bit microcontroller. So that is depending on the data bus. Okay, so you always have to look at the data bus. So that is nothing but the amount of data your microcontroller can process at that amount of time. So in the given time, how much is the maximum amount of data the controller can process is nothing but the size of the data bus. So you always have to look at the size of the data bus, or you can look at the ALU also, arithmetic logic unit also, and you can decide how much is the bitness of a particular microcontroller you are dealing with. Now look at this and tell me how much is the bitness of our PIC16 or 877E microcontroller. Okay, yes. Uh, Okay. So when it comes to the microcontroller here, which you are seeing, so if you can observe the size of the data bus, let me highlight it, or the size of the ALU, whichever you want to prefer. So size of the data bus, you can see it is 8 bits, or you see the size of the ALU, that also is of 8 bits. So our PIC16F877A microcontroller is going to have the data bus of 8 bits or ALU of 8 bits. Hence, our PIC16F877A is a 8-bit microcontroller with 40 pins involving 5 individual ports. Okay. So whenever you want to know how much is the size of the microcontroller, you can refer any of it, either the size of the data bus or with respect to the ALU. Okay. So that was about the microcontroller, the PIC16F877. Okay. Now let us get back to this. We got to know I have got 5 ports in our microcontroller, port A to port E. Now, have you got any idea to which port the LED is connected? Have you got any idea to which port LED is connected? It can be any of these ports. Have you got any idea of to which port this LED must have been connected? Input, all of these are input output ports only. So all port A to port E, all the ports are input output ports only. To which port do you think the LED is connected? Do you know, like, can you guess to which port the LED is already connected? Can you guess to which port LED is connected? So obviously no. Just with the guessing, you cannot tell to which port LED is connected. It can be connected to any of these ports. Now, in order to know how the connection is being made on the board, okay, so whatever programming we are doing is on the board, the Pixim Lab board. In order to know how the connection is already being made on this board, you have to refer one more document. So if you want to know the information regarding the microcontroller, you have to refer the data sheet. If you want to know how the circuit connection is being made, okay, so to know how the circuit connection on board is being made, okay, so you have to refer one more document, which is nothing but, I would say, refer schematic. Okay, so refer schematic of the board. So you have to refer the schematic of the board. Now the question comes is how to take the schematic of the board. So you can go for the Pixin Lab. Okay. So when you go to the help, okay, when you click on the help, you can also go to about board. Okay. So sorry, you can go to help and you can click on boards. Okay. So open Pixim Lab board. First of all, whichever board you want to deal with. Actually, this supports multiple boards. Okay. This Pixim Lab board supports multiple boards. So first you have to go to boards and select Pick Genius, because I'm going to configure a Pick Genius board, a board which involves a Pick microcontroller. When you open the Pixim Lab board, first go to board and click on Pick Genius. Okay. So whenever you want to know things with respect to the board, first open the Pixim Lab board software, go to the boards and click on Pick Genius. Now you will be able to program multiple microcontrollers which belongs to the Pick Genius. So in that you have to select PIC16F877A. I hope you are able to follow. Under boards, it has to be Pick Genius, and under microcontrollers, it has to be PIC16F877A. Once you have properly selected, you can observe that here at the top of your tool. So it says Pixim Lab, Pick Genius, the PIC16F877A. Okay, so it is going to clearly show you that. So you first make sure you are leading to the proper microcontroller which belongs to the PIC genius. Then you can go to help here. Okay. Okay. So now we have to go to help and we have to be clicking on boards. Okay. So click on help and click on boards. Now it will take you to the multiple PICgenius board. So we are concentrating on PIC16F877A only. You have to check if the name of your controller is available. So it says the PIC16F877A here. So you can scroll down and you can click on Pick Genius Schematic. So here you can see board Pick Genius Schematic. So if you click on that, you will get a page loaded. So for that, you should have active internet with you. Okay, so there should be an active internet available. If not, whenever you open this page, you can keep it downloaded because this is the one we are going to use throughout the module. So we will be programming the same board and you will need the schematic again and again. So if you don't want to make use of the internet every time you are using it, you can keep this document downloaded for your use later. Now I'm going to zoom here. Okay. So I am going to show you how the LEDs are connected and how other peripherals are connected. Now, this is the microcontroller, the PIC16F877A. One second. Okay. So here is the microcontroller, the PIC16F877A microcontroller. One second. Okay. So you can see I have got 5 ports. So this is port A. Okay. This is port A. If you can observe, this is port B. This is port C. This is port D. This is port E. Okay. So according to the number of pins of the ports, the pins are also named here. Now, how to understand this connection is they cannot make direct connection to the pins here. So in that case, the schematic looks very clumsy. Okay. So that is why they have separated their representation. If you can observe, see, there is one peripheral which has been connected to RC3. So this connection, you should assume it is at this point of the microcontroller. So from RC3, it has been connected to a device and one more is going to the ground. So this is how you have to understand. So for example, if you see, it's pick 18F. No. So this you don't worry. Okay, this the schematic is remaining the same for multiple microcontrollers. Okay, so the schematic is going to remain the same for multiple microcontrollers. This one. So this is not the one we have to refer because we have 5 ports. So this is the microcontroller which we have to be referring. The schematic, if you see, okay, when you go to help and go to boards, so that schematic holds good for any of these microcontrollers. 16F77, 16F877A, then 452, then 18F4520. So for multiple microcontrollers, the schematics are being the same. So don't worry about it. So this is the schematic we are going to refer for the PIC16F877A microcontroller. One second. Okay, so this. Now observe and tell me. I hope you remember how to represent an LED. So where are the LEDs connected to? So observe this and tell me to which port the LEDs are connected. to which port the LEDs are connected? Port D and port B, correct? So if you look at the board also, we have got 16 LEDs. Let me show you here. So here are 8 LEDs. Here are another 8 LEDs. So in total we have got 16 LEDs on our board. So where are these 16 LEDs connected is, if you can observe here, one set of LED. Okay. So 8 LEDs are connected from RD0 to RD7. So you can establish the connection. You can see it like this: RD0. Then this is RD1 connection is made to this. This is RD2 connection is made to this. So like that, because you didn't want things to look clumsy, they have shown it like this. But remember, one set of LED is been connected from RD0 to RD7. Another set of LED is been connected to RB0 to RB7. Are you able to observe it? Okay. So I will give a name for this just for the sake of reference. I will call this first set of LED as LED array 1. Okay, so first set of LED I call it as LED array 1. Another set of LED I will call it as LED array 2. Okay, one set of LED I am keeping it as LED array 1. Another set of LEDs I am keeping it as LED array 2. So what I am supposed to do here is, whichever LED I have to turn it on, I have to be providing 1 to that particular LED. Okay. So whichever LED I want to turn it on, I have to provide 1 to that particular LED. So like this, I want to turn on all 8 LEDs of LED array 2. I have to be providing 1 to all the pins. So RB0 I have to be providing 1, RB1, RB2, RB3, RB4 up to RB7 I have to be providing a 1. So earlier my program was to turn on only one LED. Now I will change the program. Okay. So my program is to turn on all 8 LEDs of port B. Okay. Program to turn on all 8 uh, LEDs of port B. Okay. So I have to turn on all 8 LEDs of port B. Now I'm going to write a new program. So void main. So return type is void. Okay. Now I told you to turn on all 8 LEDs of port B. Every pin of the port B has to be returned with 1 1 1 1 1 1 1 1. So I will write something like this: int port B. Okay. So port B is equal to binary 0B 11111111. Okay. So this is what I'm going to write. I want to turn on all 8 LEDs of port B. Okay. So what is port B having? Port B means it is having 8 pins inside it. Okay. So port B means it is having 8 pins. The 8 pins are RB7. I will start it from MSB. RB7, RB6, RB5, RB4, RB3, RB2, RB1 and RB0. Okay. Now when I write port B with the value, let's say binary 1, 1, 1, 1 second, tab, okay, 1, 1, 1, 1, 1 and 1. Now did I not end up providing 1 to the 8 LEDs which are connected to port B? So when I write port B is equal to 0B 11111111, did I not end up writing 1 to all 8 LEDs which are connected to port B? Am I right or wrong? 8-bit port, so data type how int. You can go for character also. So if you don't want to go for int, you want to save some space, you can go for character also. Okay. Now, yes, I was saying, if I write port B with 0B11111111, Did I not provide 1 to all 8 LEDs of port B? Yes, I have. So if you can observe, port B means RB0 to RB7. So I have provided 1 to all 8 LEDs of port B. Now if I execute this, okay, so if I am going to execute this, tell me, will it work fine if I execute this on my microcontroller? Will it work fine? Okay, why do you think it's a no? Yes, it's a no because I'm still not referring to the port B of the microcontroller. If you observe, port B is still a variable in my program, right? So if you observe here, I'm not referring to the port B. Okay. So port B is still a character variable. So it doesn't matter whether I take it as unsigned integer or signed integer or character. I'm not actually referring to the original port B. I'm still referring to the a variable called port B. So if I execute this program on my microcontroller, will it consider this port B as an actual port B? Will it consider this as an actual port B? No. So we are still referring it to be port B itself. Now even before that, okay, so even before that, if you have to see the port B, okay, now observe this schematic, observe this data sheet. Tell me, what are the directions of the pins of the ports in our microcontroller? 0B means binary. Okay, no other, nothing special. 0 means binary. Okay, I was asking, what do you think is the direction of the pins here? Bidirectional. Okay, the pins of the port B are bidirectional. Okay, so pins are bidirectional. That means you can configure this pin as an input pin or you can configure this pin as an output pin. So it completely depends on the peripheral you are configuring. So you can configure this pin as an input pin or you can configure this pin as an output pin. Okay. Now, how to tell whether the pins of the port should be treated as input or it has to be treated as output? So, because they are bidirectional pins, I cannot use them both as input and output at the same time. You either can use the pin as an input pin or you can use it as an output pin. So how are you going to use it? Whether you will use it as an input pin or you are going to use it as an output pin. So that is, you can know, I'll take you to another information. So I want to know things with respect to port B. I want to tell how the pins of the port B has to be treated. So I will go here and search for port B. Okay. Now let us see where and all I can find port B. I'm scrolling down. So I want some information regarding port B. So I am looking into that information. Okay. So still the words port B, port B. Okay. Now see here. I came up to this port B and TRISB registers. I will highlight certain points. Please read that much and let me know once you're done. From here, you please read up to this. So I have highlighted certain part. Please read it and let me know once you're done. Done? So fast? Okay. Fine. So those who are done, can you see that when you are talking things with respect to port B, It is also talking things with respect to another register called trisb. Do you see that? So when you are discussing things with respect to port B, it is giving you things with respect to another register called trisb, which is called as the data direction register. Okay. So remember, there is something called as a data direction register. Okay. So we call it as DDR, which represents data direction register. Okay. Now what is this data direction register is? It is represented by tris. Okay. Tris, I would say X. Okay. Because it is tris A for port A, tris B for port B, tris C for port C, tris D for port D, and tris E for port E. So I will write it as tris. Now what is this tris is? It represents tri-state. Okay. So tris means tri-state. Tri means how many? So tris means tri-state. Tri means three states. So using the tris registers, you can represent three states of a pin. One is the state called input, other is the state called output, and one more is the state called high impedance. So these are the three states which can be represented by a particular tri-state register. Now, whenever you want to represent the direction of a pin as input, you have to write a 1. The direction is output, you have to write a 0. If you neither write a 1 or a 0, it will be by default in the high impedance state. Now, what exactly does that mean is, I have RB7 pin of port B. Okay, there is RB7 pin of port B. How do you want this RB7 pin to be treated as? Whether you want this RB7 pin to be treated as an input pin or you want it to be treated as an output pin. Okay, so that is said with the help of tris register. Okay, so that is said with the help of tris register. Now what is the tris register associated to port B? What is the tris register associated to port B? Yes. What is the name of the register associated to port B? So it has to be tris B. Okay. So it has to be tris B. Now tris B also has 8 pins associated to it. So it starts from tris B7, the most significant bit. Okay, 1 second. Tris B7, then tris B6, then tris B5, tris B4, tris B3, tris B2, tris B1, and tris B0. Okay, so I'm going with these tris registers. So remember, tris B also has its pin. Okay, the whole register's name is tris B. But if you want the pins of that tris B register, it is tris B7 to tris B0. Now, whenever I write the corresponding tris register with 1, the corresponding port pin will be treated as input. So, for example, let's say to the tris register, I'm writing 1, 1, 1, 1, 1, 1, 1, 1. So, what do you think this statement says? So, assume I write tris B is equal to 0B 1, 1, 1, 1, 1, 1, 1, 1. Okay. So what is it making? When I write tris B with 0B 1, 1, 1, 1, 1, 1, 1, 1, I'm writing tris B7 to tris B0 with the value 1. That means the direction of tris B7 is for RB0. So for RB6, you're using tris B6. So RB7 to RB0, what am I setting? RB7 to RB0 should be treated as input. Okay, it has to be treated as input. Now, one more example. I will write tris D7 with the value 0. So, what do you think this does? Tris D7 is written with 0, correct? Output. Which pin is made as output? Which pin is made as output? 7 of what? Seventh pin of what? Seventh pin of which port? Yes, it is port D because I'm using tris D. It is port D. Seventh pin of port D is what? It is RD7. Okay. So if I write tris D7 with the value 0, RD7 is treated as output. Similarly, assume I write tris C is equal to 0x F0. Can you now tell me what is the direction of which pins I'm talking about? So I'm writing tris C with the value 0xF0. Upper nibble input, I want to know the names of the pins. Okay. Yes. So always started from the MSB. Okay, started from the MSB. So 0xF0's binary representation is 11110000. Okay, so binary representation is 11110000. So this 11110000, what I'm trying to do is, okay, so this is RC7. This is representing tris C7. This is representing tris C0. So RC7, okay, to RC7654, RC4 is being treated as input. Okay, then RC3 to RC 0 is being treated as output. Are you able to follow this? Everybody? Okay. Now I will make one more assumption. So assumption number 1 I made was LED return with 1 will turn it on. Assumption number 2 I'm making is whenever I'm using the LED, okay, so while using LED, okay, the pins have to be treated as output. Okay, so that is another assumption. So I'm making two assumptions. Assumption number 1, so we will justify these assumptions later. Assumption number 1 is LED return with 1 is going to get it turned on. Assumption number 2 is while using LED, the pins have to be treated as output. Now we got to know that 8 LEDs are being connected to port B. Okay, so 8 LEDs are being connected to port B. I want to turn on all 8 LEDs of port B. So I will take one more character variable called tris B. Okay, so what should I write to the tris B? First of all, what should be the pins? What should be the pins direction? What did the assumption we made? What was the assumption we made? It has to be output. So RB7 to RB0 has to be treated as output. So how will you make it treat as output? Okay. So I will write TRISB with 0B 0 0 0 0 0 0 0. Okay. You either can write it like this, or if you want, you can write hexadecimal 00, or if you want, because it is 0, you can directly write 0 also. So whichever way you are convenient, you can use. Now stress B is 0x00, port B is 0B11111111. Now tell me, I have set the direction of port B pins also. If I execute this code on the microcontroller, will it turn on all 8 LEDs of port B? If I execute this on my microcontroller, will it turn on all 8 LEDs of port B? Still no, because port B and tris B are not the registers I am referring, they are still the variables. Then how to refer port B and tris B registers directly? So how to write into the port B, how to write it into the tris B register? So that is with the help of a register file map. Okay, so you can search for a register file map. So I'll go here, register map. Um, okay, so I'm searching for register file map. So all of these are registers only. I'll directly go here, register file map. Okay, so register file map of PIC16F877A is in page number 17. Okay, here it is. So look at the register file map of the PIC16F877A microcontroller. What is the address of the register port B? What is the address of the register port B? It is 06H. And what is the address of register tris B? What is the address of the register tris B? It is 0x86H. Okay. So actually, if you think, there is a register called port B. There is a register. Whenever you want to write into a register called port B, you have to write it into a register which is in the address. So this is one register, this is another register. Two addresses per register. You don't look at the second address because that is referring to an instruction set, the ones which you don't use to handle the data. So that is to handle the instruction. So don't look at the second address. It is always the first address you have to see. Okay. Now, there is a register at the address 0x06. So 06H means hexadecimal. So there is one register at the address 0x06. So whenever you want to write it into port B, you have to write it into the address 0x06. So one more register is in the address 0x86. So whenever you want to write it into the register tris B, you have to write it into the address 0x86. Okay. So whenever I want to write it into port B, I have to write it into the address 0x06. Whenever I want to write it into the register tris B, I should write it into the address 0x86. Now what should I use to go and write a data into a address? So what do I need? I need a pointer variable. So first I'll take an unsigned character pointer called port B. Okay. at the address 0x06. 0x06. Okay. So in order to avoid the inconvenience, I will also typecast it. So unsigned character pointer. Okay. Then after this, I will take unsigned character pointer called trisb. Okay. Return with unsigned character pointer 0x86. Okay. Now I want to write it into the trisb register. How to write? To the trisb register, I should write the value 0x00. To the port B, I have to write 0B 11111111. Can you tell me how to write it now? Yes. See, instead of this, I'll take unsigned character pointer called port B. Wait. Unsigned character pointer called port B. Return with address 0x06. Then trisb return with 0x86. So whatever I want to write to trisb, I'll write star trisb, and this has to be star port B. Okay. Now see, whatever I wanted to write to port B, okay, I'm writing it into the address 0x06. Whatever I wanted to write into trisb, I'm writing it into the address 0x86. Now tell me, if I execute this code on my microcontroller, do you think it will turn on all 8 LEDs? If I execute this code on my microcontroller, will it turn on all 8 LEDs of port B? Yes or no? No? Why is it still a no? May I know the reason? As of now, no, you don't have to need any headers inclusion. And trust me guys, if you execute this code on my microcontroller, it will definitely turn it on. Okay. See, our intention was to turn on 8 LEDs of port B. Okay. So I'll rephrase this. I wanted to turn on 8 LEDs of port B. Its data direction register is trisb. Okay. Its data direction register is trisb. So I wanted to write port B with 0B11111111 because I have to turn on all 8 LEDs. Now while LEDs are used, the pins of the port has to be set as output. So I had to write trisb with the value 0x00. Now what happens after these two? So I wanted trisb to be written with 0x00 to set RB7 to RB0 as output. I wanted to write port B with 0B11111111 because I want to turn on all 8 LEDs connected to port B. So this program, if you execute, it will definitely work because whenever I want to write it into trisb, I'm making sure I'm writing it into the address 0x86. So that is the register where the trisb is available. And whenever I want to write to port B, I'm writing it into the address 0x06. So that is how you are directly writing to the port B. Now if I execute this code on my microcontroller, it will definitely work. But the problem is, don't you think whenever you have to write to a corresponding port or whenever you have to write to a corresponding trace register, again and again you have to search the address where the register is available and you have to write. Don't you think it is time consuming? So it is always time consuming. That is why we have a header which has the macros already written. So you can just include a header called xc.h. Okay. So here you can include a header. Include a built-in header called xc.h. Okay. And whenever you want to write to port B, you directly make use of the name of the register. So you can write trisb and you can write port B here. And it is case sensitive. Okay. So macros are already available. When you write trisb, okay, due to the header xc.h, there is a macro called trisb. You are ending up writing into the address 0x86. Similarly, when you write port B, okay, so you are ending up writing into the address 0x06. So that is why I said the names of the registers are very important to be remembered, very important to be properly specified. So because the names of the registers remains the same in the headers also you're going to use. So trisb, if you write 0x00, you are ending up writing it into the register at the address 0x86. Port B, you are writing it into the address 0x0. Now don't you think it is easy? So whenever you want to write to the trisb register, make the name taken. Whenever you want to write to the port B register, write the name. So this is the simple program which is used to turn on all 8 LEDs of port B. Okay. Now if you want the same to be done for port D, what will you do? I have to turn on all 8 LEDs of port D. Now if it is port B, I want it to port D. So here you will make port D is equal to 0xFF. What about its trace register? Will you only change the port B to port D? You also have to set the direction of, okay, so you also have to set the direction of the pins of the port. So this also has to be trisd. Ma'am, can you please pardon from where we get 0x06 and 0? Okay. So that is from the register file map of your microcontroller. So register file map will be available for all the microcontroller. So port B is in the address 0x06, trisb is in the address 0x86. And this is the very simple program which is used to turn on all 8 LEDs of port B. So for port D, instead of trisb, it has to be trisd. Instead of port B, it has to be port B. Please explain 0. This is not an address. This is the value you want to write to the trisb register. To the trisb register, I have to write 0x00, means 00000000. So that I have written in the hexadecimal format. That's it. Okay. Any doubts? Is this much clear? Okay. All right. So we will continue in few minutes. We will take a break of 2 minutes and we will continue. And if you have got any doubts, please post it here in the chat box. We will take a break of 2 minutes. Okay, xc.h header file is same for microcontrollers, or will it change depending on the IC manufacturers? So that xc is a header for the xc 8 cross compiler. So whichever microcontrollers will be supported, okay, it depends on one platform to another. So I am using MPLAB IDE, and along with that we are using the XSC8 cross compiler. For that we need the header called xsc.h. So this xsc.h is a cross compiler which can convert a high level language to a machine level language for multiple microcontrollers, not just for PIC. It can convert it for multiple microcontrollers. You have to look at the user manual while you are choosing the cross compiler, and then you have to decide which header to be included. So depending on the cross compiler you are using, depending on the microcontroller you are using, you will have to choose different header file. Okay, any other doubts? Okay. Fine. Port B should have 1 at all bits to glow the LED, but tris B should have 0 at all bits to glow the LEDs, right? Okay. So that is because, yes, that is right. Port B should have 1 return to all the pins, and tris B should have 0 return. So tris B is returned with 0 because you are setting the direction for the pins of port B. So if you write tris B with 0, the pins of port B will be treated as output. So due to these two assumptions we made, okay, so LED has to be returned with 1 to turn it on. So I wrote every pin of port B with 1. So while using LED, the pins have to be treated as output. So RB0 to RB7 to be treated as output, you have to write tris B0 to tris B7 as zeros. So that is why we wrote tris B with 0 and port B with 1. Clear? Okay. All right. So let us continue. So we made two assumptions here. Okay, that LED has to be returned with 1 to turn it on, and tris B has to be returned with 0, that is the pin have to be treated as output. Now let me justify these 2 points now, and then we will proceed. To make a justification, I will first show you a picture. Give me a second. Hmm, Okay. So I'm showing you a picture right now. Please look at this and tell me, do you consider this as a LED? Is this an LED I'm showing right now? No. So that is in fact just a diode. Okay, it's not an LED. It is just a diode. Then what do you mean by an LED? What do you mean by an LED? If this is not an LED, what exactly is an LED then? Light emitting diode. Yes, you have to go for an output raise. Can I now call this as a LED? Okay. So LED means it is a form of a diode, but it emits light whenever the current passes through it. Okay. So LED is nothing but light emitting diode, the one which emits light whenever the current is passing through it. So this is a LED. Now in this LED, if you observe, okay, this is a light emitting diode. There is light being emitted by the diode. Now in order to make this LED glow, what sort of circuit connection should we be making? To make this LED glow, what sort of circuit connection should we be making? A battery. Okay, is that okay? So you have to provide a power supply. Have you heard of two ways of making a connection? Like we call it as a forward biased connection and a reversed biased connection. Have you heard of it? Okay, if yes, how should you make the connection? Is it a forward biased or a reversed biased connection? It should always be a forward biased connection. Now, what is a forward biased connection is? Positive of the LED should always be connected to the positive terminal. Negative of the LED should always be connected to the negative terminal. So that is forward bias. Reversed bias means positive of the LED will be connected to negative. Negative of the LED will be connected to positive. So that is reverse bias. Okay. So we should always make sure that the connection is forward biased so that the LED is glowing. So this is still not an LED. I'm going to add arrows to it. So now I can refer it as an LED. So this is forward bias because positive of the LED is connected to the positive voltage supply. Negative of the LED is been connected to the negative voltage supply. Okay. Now, if I take this circuit, do you see any potential issue in the circuit? Potential issue in the sense, an issue which you may come across going ahead. Okay, it's an issue you may come across going ahead. Yes. So what happens if more than required current is flowing? Okay. So what happens if more than required current is flowing via this particular resistor? Particular diode. So obviously it is going to get damaged. Okay. So the LED is going to get damaged. Then how to sort this out is, you have to add a passive device which consumes the current, and you should not let the device get damaged. So I should have a resistor added. Now you should make a small self study if you have forgotten how to add a resistor and all. So that is not our focus right now. So I'm going to add a resistor in series. Okay, and it doesn't matter whether I add it before the LED or I add it after the LED. So I'm just adding a resistor now. Now the circuit is perfectly fine. So whenever current flows through the LED, so LED is going to get glown. Okay, so that is nothing but the connection. Okay, now observe. One second, I'll take you to the slide. Give me a second, I'm just trying to load. Hmm. Give me a second, guys. I'm almost done. So I just wanted to show you a representation. It is taking time to get loaded. Okay. Okay, so LEDs is what we are talking about. Okay, so first I think I should have to take up this slide. So LED is nothing but the simplest device which is commonly used as a feedback device. It's a simplest commonly used feedback device which works exactly like that of a diode. The advantage of LED is it consumes very less energy, so it has got a longer life. It is comparatively smaller in size and it has got the faster switching, which is why it is very widely applied on home lighting. So you will use it in home lighting. You will use it in remote controls and surveillance. You will use it in displays and many more. So these are the places where LEDs are used. Now observe two connections. Okay. So you can say the left one as connection A and the right one as connection B. Now think and answer. When you press the switch, which LED is going to get glown? Whether it is LED A or LED B. When you press the switch, which LED is going to get glown? Whether LED A or LED B. Now for that you have to remember the longer leg is said to be positive and shorter leg is said to be negative. Okay, shorter leg is negative, longer leg is positive. So for the LED to glow, positive has to be connected to positive and negative has to be connected to negative. You have to establish a forward bias connection. Now observe how this is going to work. So in the first case, if you take scenario number one, okay, switch is pressed, positive is being connected to ground and negative is being connected to positive. You can see this is the negative of LED which is being connected to positive and this is the positive of LED which is being connected to negative. Do you think I have formed a forward biased connection here? Have I formed a forward bias connection? No. So LED is not going to glow. So if you go with the second scenario, you can see LED is glowing a little brighter this time. So that is because when you press the switch, positive of the LED is being connected to positive voltage supply. Negative of the LED is being connected to the negative, which is ground. So there is forward biased connection established, which is why you can see that the LED is glowing. Okay. Now, I told you that we have got two different, we made two assumptions, if I'm not wrong. So let me make you understand what exactly or why exactly did I make that assumption. So to start with, remember an LED can get connected to a microcontroller in two ways. Okay. So I'm taking one way of connection here. This is for another way of connection. So this is your microcontroller, the PIC16F877A microcontroller. Okay. So LED can be connected to a microcontroller in two different ways. So I'm drawing that. So it takes time for me to draw this. Okay. So on the left hand side, what you see is one way of doing the connection. On the right hand side, what you see is another way of doing the connection. Then this is register. Please assume it to be a register. This is an LED. I have to go with arrows also. This is an LED. This is arrow. This is register. Okay. Now, always for the LED to be glown, you have to establish a forward biased connection. Okay. So you always are supposed to establish a forward bias. This is the positive. This is the negative. Negative is already been connected to negative here. Okay. So negative is already been connected to negative. To establish the forward biased connection, what should I be providing here at the pin of the microcontroller? To establish the forward biased connection, a positive have to be connected to a positive supply only. And positive supply means it is 1. So it is either VDD or VCC or 5 volts, it is 1. So to turn on the LED, so you have to be providing a 1, and to turn off the LED, I have to be providing a 0. Do you agree? So to turn on the LED, I have to provide a 1. In this case, to turn off the LED, I have to be providing a 0 because I have to establish the forward biased connection. Negative has already been connected to negative. You have to make sure positive is connected to positive. Similarly, in the second case, this is 5 volts. Okay, this is 5 volts. So positive has already been connected to positive. I have to make sure negative is being connected to negative to establish a forward bias connection. So to turn on the LED, what should I write? To turn on LED, what should I write? I have to be writing a 0. And to turn off the LED, I have to be writing a 1. Okay. Now, this kind of circuit, what is happening here is the current from the VDD is flowing to the ground. I mean, the current from the microcontroller is flowing to the ground. Do you agree? So current from the microcontroller is flowing to the ground via the LED. So here your microcontroller is acting as a sourcing circuit. So this kind of circuit is called as current sourcing circuit. Okay, this is current sourcing circuit. Similarly, in the second case, current is flowing from the VDD or VCC into the microcontroller. So current is being taken by the microcontroller. Hence, this circuit is called as current sinking circuit. Okay, this is called as current sinking circuit. This is sourcing circuit. This one is sinking circuit. Think and answer. In our circuit on board, okay, you saw the schematic. Okay, in our circuit connection, whether we have a sourcing circuit or a sinking circuit, what do we have? Whether we have a sourcing circuit or a sinking circuit. Yes, what we have is a sourcing circuit. And because we have a sourcing circuit, to turn on the LED, we are providing a 1. To turn off the LED, we are providing a 0. Do you get this point? Are you people? Okay, so that was the first assumption we made. The very first assumption we made was to turn on the LED, we have to be providing a 1, and to turn off the LED, we have to be providing a 0. So that is because what we have is a sourcing circuit on our board. So to establish a forward biased connection, I have to be providing a 1 to the pin of the microcontroller to turn it on, and I have to provide a 0 to turn it off. I hope you are following this. And the second assumption we made was I have to treat the pin of the microcontroller as output. Now think of this pin. So whether it is in the input or the whether it is in the sourcing circuit or the syncing circuit, how is this pin acting as to the LED? How is this pin acting as in the LED? So to this LED, whether you take LED 1 or you take LED 2, how is the pin acting? The pin is an LED to the LED, the pin is an input. Okay, so to the LED, the pin is an input. You provide one, LED gets turned on. You provide 0, LED gets turned off. So to the LED, the pin is acting as an input, but the direction of the microcontroller is always opposite to it. Okay, direction of the microcontroller is opposite to it. The pin is serving as an input to the LED, but with respect to the microcontroller, it is always opposite, which is output. So in both the cases, whether it is the syncing circuit or the sourcing circuit, the pin direction has to be output. Got it? Is that clear? Okay. So that was the two assumptions we made with respect to the LED. I hope you are clear with this. Any doubt? Okay, fine. So let me take you to the slides back. So this is the circuit which is present on our board, which is a sourcing circuit, and the direction of the pin should always be output when it comes to the LED. Let me actually go out with one small program, one small topic. So projects creation. So that was the basic of the LED. Here I'm showing is whenever we are going to have our project created in the IDE, we will have a habit of taking separate .c files and separate .h files for every peripheral we will be programming. So when to go with a separate .h file, when to go with a separate .c file, I'll guide you accordingly. You can consider. But we will have a habit of writing it in individual files for the sake of proper documentation. Then this is how the template code looks like. So we will follow this going ahead. First is your main.c file, which has two functions. One is the main function, the other one is the init config function. So main function is like the basic main function. Init config function is the one which we use to do all the basic initializations. So I understand you can do the same in the main function itself, but still we will have it written in a separate function just for the proper representation. So any basic initialization we want to do, we will do it here in the init config function. Okay, for example, I want to set the direction of the pins of a particular port, or I want to do the basic initialization of the pins of a particular port. So all that I will write it in the init config function. Okay, separate function to do the basic initialization. And that function we will call it in the main function. And whatever application I want to implement, I will have it written inside while of one, because any embedded system you are trying to write, once it starts, will it stop by itself? So once it stops, will it stop by itself? No, right? So any embedded system, you take your smartwatch, you take your refrigerators, you take your washing machines. Unless you forcefully turn it off, it will not get turned off. Anything you are going to turn it on, it will be running for its lifetime, which is why any application we are going to implement, we will have it return inside our while of one. Okay, so we will have it return inside our while of one. Then this is the main functions template. So you will have init config function to write the basic initialization. You do the init config functions call being in the main function. Now this is the header file, and we will follow this way of including the header. So why do you think we are writing like this? We have already known it in our C programs also. So why am I doing it like this? Okay. So just to make sure that the header contents are included for only once. Okay. So even if you try including the contents of a header for multiple times, you have to include it for only once. Okay. So that is why, remember, whenever you have to include a header, you will include it for only once with the help of something called as conditional compilation. Yes, to avoid redefinitions and all, we will use this conditional compilation. If not defined of a macro, you define a macro, you include the contents of the header, and you terminate the end. So like this, we will have separate .c files and separate .h files created going ahead. Any doubts? Okay. So actually, these are the interfaces we have got on our board. We have LEDs, we have digital keypad, interrupts, timers, clock input output, SSDs, CLCD, matrix keypad, analog input and all. And we can use header files with codes too. Yes, you can. So like as a good representation, we are having it in a separate file written. That's it. Okay. And we saw things with respect to the LED. So the next we have to learn is how to make use of the tools. And I cannot be starting it now because I will not be done if I start it now. So tomorrow, I mean on Monday's class, we will start how to make use of the tools and we will execute our program. So on Monday's class, we will be done with the LEDs. Okay. So on Monday's class, we are going to start with how to make use of the tools, how to execute the code on your microcontroller, and we will see few more programs associated to the LEDs on Monday's class. So I'm going to wind up the class today here. Any doubts? Okay. So to summarize today, we just looked into the trace registers, the port registers, and the basics of LEDs. So Monday we will be done with the first peripheral LED, and from Tuesday you can start working on the assignments on LED. Okay. Hope the class is all being cleared. Please do wait. You have to mark your attendance before quitting. Can we have the link in the chat box to mark the attendance? Oh, you want it? Yeah, I'll do that. Okay, so here is your QR. Please have your attendance mark before quitting the session. Thanks for attending today's class. We will continue on Monday. Thank you all.